So this section is about the monotonicity and the first derivative test. So the a function f is increasing on an interval if for any two numbers x1 and x2 in the interval, x1 less than x2 implies that f of x1 is less than f of x2, and a function f is decreasing on an interval if for any two numbers x1 and x2 in the interval x1 is less than x2 implies that f of x1 is greater than f of x2, and otherwise the function is monotone. So you can see what this looks like graphically down here, right? So here's a situation where the x1 is less than x2, but the f of x1 is less than the f of x2, so that means that this function is actually going up in value. And then here is a situation where x1 is less than x2, but then you can see that the function is actually going down in value. And here is a situation where the function is actually not going up or down and just stayed the same. So this is actually just constant, or what I call monotone on that interval. So that means neither increasing or decreasing. So how are you going to test for this? Well, one way to do this is actually by looking at the derivative. So if you assume that the function f is continuous on the interval I, and that f is differentiable at every number in the interval I except for possibly at the endpoints of I. So that's why if you think about, like, every time that I've talked about this, I've been talking about the a to b with parentheses at the endpoints and not brackets, because it's saying that the values here might not be at the endpoint. So the endpoints don't need to be included here. So then if the derivative is greater than or equal to 0 for every number x in the interval, except again possibly for the endpoints of I, then f is increasing on I. And then otherwise we see here is if it's less than 0, the derivative is less than 0 for every number x in I, except again possibly for the endpoints of I, then f is decreasing on I. So here is increasing the derivative greater than 0, and here is decreasing the derivative is less than 0. And try to remember that the derivative is the rate of change. So if the rate of change is positive, then the function will be going up. If the rate of change is negative, the function will be going down. And then these numbers C are critical numbers for a function f if f is not defined at C, and either f is not differentiable at C or f prime of C is equal to 0. So usually we say that a critical number is where the derivative is equal to 0, but there are other places that could be critical numbers, and that's places where the function is just not differentiable or where the function is not defined. So there's actually 1, 2, 3 things that we need to check. All right, those all could be the critical numbers. And then finally, if a function f has a relative extremum at the number c, then c is a critical number for f. So a relative extremum means that these are the relative maximum or minimum, and remember that those cannot occur at an endpoint. So hopefully it doesn't surprise you that we're not actually including the endpoints in any of these intervals, since these relative maximum minimum aren't occurring at the endpoints anyway. So let's look at an example here. So again, if you have any questions about any of this, just put that in the chat. But here, let's identify the open intervals on which the function is increasing or decreasing. So remember that a function is increasing where the derivative is greater than 0. So that would be f prime of x greater than 0. And it is decreasing where we can figure out where f prime of x is less than 0. All right. So we need to figure out the derivative here. So f prime of x is going to be the derivative of 27x minus x to the third. So it's 27 minus 3x squared. And then I will set the derivative equal to 0, and that will help me figure out the critical numbers. So the points where the f prime of x are equal to 0 are the critical points, or the critical numbers. All right, so that's why we're doing this, to figure out where the critical numbers are, or where the derivative might change from negative or to positive. So what I'll do then is I will go ahead and subtract 27, divide by negative 3 to get x squared is 9. So then I take the square root. So I know that x is equal to plus or minus 3. All right, so I know that those are actually the critical numbers. So the critical numbers in this case are negative 3 and 3. So those are the points where the derivative is equal to 0. So at negative 3 and 3, the derivative is equal to 0. And then if I look at the derivative here, the derivative is, f prime of x is 27 minus 3x squared, or that's negative 3x squared plus 27. So I know that it's a parabola opening down, and that it has a y-intercept of 27. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. All right. So if I want to draw this fairly accurately, then this is what the parabola will look like. All right. So I'm trying to find a new pen here because I actually don't even have my markers or pens or highlighters at home with me because they're still locked up at the college until, what did they say, at least April 17th now. So I'm using these dried out ones that I happened to find under the like they were behind the couch, so I don't know how long they've been there. So now we see that here is the part where the derivative is greater than 0, and here are the parts where the derivative is less than 0. All right, so this means that the f of x is going to be decreasing on the intervals where the derivative is negative. So from negative infinity over to negative 3, and from 3 over to infinity, and then f of x is increasing on the interval where the derivative is positive. So that would be negative 3 to 3. All right, so hopefully that all makes sense. That's all I did here was figure out where the the derivative was positive and where the derivative is negative. All right, so if you have any questions, again, please just ask or put them in the chat. But here is another great example here. So g of x is equal to x plus 4 over x. So first, remember that we need to find the critical numbers, and there's 3 places where that could happen. One, it's where the function g of x is undefined. Or 2, the points where the derivative g prime of x is equal to 0. Or 3, it's the points where g prime of x is undefined. So we have to check all of these. The last one happened to be a polynomial, so we weren't worried about any of the points where this could be undefined. But I noticed right away, g of x, the denominator here, x cannot equal 0. So x equals 0 is one of the critical numbers. All right, now I need to find g prime of x. So here we go. So g prime of x is equal to x plus 4 over x, or that's actually 4x to the negative, sorry, that's g of x. So I was going to write g of x over here, and then I realized I didn't. So g of x is equal to x plus 4x to the negative 1 power. And so that was, again, originally what I was going to write over here, and then I realized I didn't. So now I can find g prime of x. So the derivative of x is 1, and the derivative of 4x to the negative 1 power is negative 4x to the negative 2 power, or 1 minus 4 over x squared. I would always recommend that you go ahead and you make sure to rewrite this derivative without negative exponents, because it will make it easier to see the points where the function might be undefined. If you leave it as a negative 2 exponent, then you might actually not recognize that that was supposed to be undefined at this point at x equals 0. So g prime of x is undefined at x equals 0. So there we go. And now we need to figure out the points where g prime of x is equal to 0. So we're going to have g prime of x equals 1 minus 4 over x squared and set that equal to 0. I'm going to subtract the 1, so negative 4 over x squared equals negative 1. Then multiply by the x squared, so negative 4 is negative x squared. Divide by negative 1, so 4 is equal to x squared. Then I take the square root, so plus or minus 4 is equal to the square root of x squared, and the square root of 4 is 2, so plus or minus 2 is equal to x. So there are 2 critical numbers here, negative 2 and 2. All right, so what a time to be alive. All right, so now, let's see. We can graph the g prime of x to figure out where the derivative is greater than 0 or less than 0, because remember that g of x is increasing if g prime of x is greater than 0, and g of x is decreasing if g prime of x is less than 0. So I know that the derivative is actually equal to 0 when x is negative 2 or 2, and I know that this is undefined at x equals 0, so there's an asymptote here. And then I can go ahead and graph a point if you would like, but I hope that you can see. Let's say that you make a table, right? And this is x, and there's the derivative 1 minus 4 over x squared. If x is negative 1, I have 1 minus 4 over negative 1 squared, and that is going to be a negative 3. So negative 1, negative 3. So I know that the graph needs to go like this. And then at 1, I have 1 minus 4 over 1 squared, that's negative 3. So I know that the graph needs to go like this. And then I can tell right away where the derivative is going to be greater than 0, right here and right here, and where the derivative is going to be less than 0, right here and right here. So, well, there goes my marker. That's okay. But yesterday, the lights were going in and out. And because my basement lights are actually on a 60-minute timer. So how do you know there's an asymptote? So I will come back to that in a moment. But for the time being, like I know that based on this, g of x is actually increasing on, all right, the intervals from here was negative 2, here was 2, so negative infinity to negative 2, and 2 to infinity, and g of x is going to be decreasing on, so decreasing on the negative 2 to 0 or 2 to infinity. So I do know, for one thing, that this is actually undefined. The derivative is undefined at x equals 0. But one of the common shaped graphs that sometimes people know, like if I just take a look at 1 minus 4 over x squared, that's g prime of x, right? So that's the same as negative 4 over x squared plus 1. All right, now what I need you to sort of remember is the basic graphs that people may have shown you in the past. Like you have g of x is 1 over x, so that would look like this. This is a basic graph, right? And then g of x is equal to 1 over x squared, all right? This would actually look something like, yeah, this is actually one of those interesting ones because it would go like this, all right? And then if I do the reflection, the negative 1 over x squared, then these actually get reflected, so they look like this. All right, and then I happen to know that this was actually just shifted up 1 unit, so that's why it actually ended up crossing over the x-axis so soon here. So this is just a property of these basic graphs that we've been talking about with the limit as x approaches 0 from the let's say the left, or from the left, all right, of say 1 over x. So that would be, well, that would be negative infinity. So therefore x equals 0 is a vertical asymptote. So I went back to the shape of the basic graphs to know in my head that something over x squared would give me the vertical asymptote there. So hopefully that answered the question. And if there's any other questions, please feel free to ask. But I'm hoping that no one needs that page anymore, because I'm going to look for the next page here, and that would be the yeah. So okay, so no. So that's not actually the. That's actually not the. Okay, so I see that the question there about the graph of the line. So like these, like I actually am not, by the way, like I'm not actually labeling these like in for any certain purpose. All right, so I'm actually labeling it like arbitrarily. So maybe I shouldn't have used the same letter. Like if I say this is what f looks like, and this is like what h looks like, and this is what k looks like. I'm just using the shape of these graphs to figure out what the function looks like. So, by the way, this is something that's, I think, important in a way here, because if you look at it, all right, so why are we using the graph of the function in some cases and the graph of the derivative in some cases? Well, the point is actually this. It's that we're going to use the derivative to graph the function. All right, so let's look at this. Like, let's say you had g of x is equal to x plus 4 over x, and you had what we had, g prime of x was 1 minus 4 over x squared. All right, so I already showed you what this graph looked like. It looked like this. All right, and here it is. So it looked like this. This was g prime of x. Now, let's say that I wanted to find the graph of g of x. So I know that x cannot equal 0. So if I graph this, x plus 4 over x, and I'll just show you what the calculator looks like just so that you're aware of this. So hopefully you see that it has a slant asymptote of y equals x, because the limit as x approaches infinity of x plus 4 over x is x plus 0 is x. So there's my slant asymptote. All right, and I know that it has a vertical asymptote, and so what I'm actually doing then is just drawing this somewhere in the middle here. But I know from the graph of the derivative that from a negative infinity to negative 2, the graph needs to be increasing. So that's how I know that from negative infinity to negative 2, the graph needs to go up. And then at negative 2, the graph switches to being decreasing. So that's when this turns around and starts to go back down. So here was the increasing, and here was the decreasing. All right, so that's why we use the derivative. So there we go. Now I know that from the derivative from 0 to there goes the mouse too. All right, so let me. It's not a real mouse. I mean the computer mouse. So don't worry. I don't have any rodents in the house, at least not yet. All right, so. You never know, like with the way the world is going, if the trash pickup ends, and everyone's going to have rodents in their house. So there we go. So from 0 to 2, the graph of the function is decreasing. So I know that I have to come down here. So here's the decreasing part. And then after that, the graph starts to go increasing again. So then here, the graph at 2 needs to turn back around and be increasing. Now, hopefully that answered the question, but if it didn't, you can ask again. But the fact of the matter is then there's a connection here if you haven't actually realized it yet. This is where g prime of x was equal to 0. It was at x equals negative 2. And here is where g prime of x was equal to 0 at x equals 2. Okay, so those are the points where there's going to be a relative minimum or a relative maximum. The points at where the derivative goes from negative to positive or positive to negative, or where the function is going from increasing to decreasing, that means if it's going up and coming back down, that it's reached its maximum. Or if it's going down and then coming back up, it's reached its minimum. All right, so that's why sometimes we look at the graph of the function, and sometimes we look at the graph of the derivative. But in terms of like the lettering, it's just whatever letter I want it to be, like F or K or H or G. So there you go. So that is like since you can't get into the DIA right now, you can just like take a screenshot of this and put it up on your wall and look at it all day. So that's something to do in your free time when you're stuck at home now. So now let's look at the first derivative test here. So this sort of is going to say exactly what I just said here, and that's if you let C be a critical number of a function f that is continuous on an open interval I containing C, and if f is differentiable on the interval except possibly at C, then f of C can be classified as follows. So if f prime of x changes from negative to positive at C, then that means that f has a relative minimum at C, f of C. So here is the diagram showing that. All right, so here's the relative minimum right here. So you can see here that's where the graph has a horizontal tangent line. All right, so from A to C, we see that the graph is actually decreasing or going down. So f of x is decreasing on this interval, but that means on that interval also f prime of x is less than 0. And then from C to B, we see that f of x is actually going back up, so f of x is increasing, and so then f prime of x is greater than 0. So if a function is going from decreasing to increasing, then that means that the graph will have f of x will have a relative minimum there. All right. So if f prime of x changes from positive to negative at C, then f of x has a relative maximum. Here it is. All right, relative maximum, and here's the point where the tangent line is horizontal to the curve here. So then it has a relative maximum at C, f of C. So you can see from A to C, f of x is increasing, and that means the derivative would be greater than 0. And from C to B, f of x is going back down, so decreasing. So that means that f prime of x is less than 0. So if a function is going from increasing to decreasing, then that means that f of x has a relative maximum. But if f prime of x is positive on both sides of C, so if you look here, right, you see that f prime of x is greater than 0, f prime of x is greater than 0. That actually, you can tell, is the case because f of x is always increasing. So if f of x is always increasing, then what does that mean? That means that f has no relative extremum. All right, so remember, because the relative extremum have to occur in the interval and not at the endpoint. So please keep that in mind as well there. So now, if it's negative, like in this case, f prime of x less than 0, f prime of x less than 0, we can see here that we have a graph that is always decreasing. So f of x is always decreasing. So this is another situation where f has no relative extremum. All right, so if you have any questions, please ask, but I'm going to find the next page here. Example here. So use the first derivative test. So remember that this test we're going to use, use to find the relative extreme values. Right? So to find all numbers at which the function has a relative maximum or minimum. So first we need to find the critical numbers. So one of the spots where that happens is where the derivative is equal to 0. So f prime of x is equal to, since f of x is x squared plus 6x plus 10, f prime of x is 2x plus 6. I set this equal to 0. So then I can see here that I have a, well, by the way, this one actually shouldn't be a surprise to you, but in either case, it's 2x equals negative 6, and x is, when I divide by 2, negative 3. So if I graph the f prime of x, which is f prime, I wrote f inverse, but it meant f prime. So f prime of x, and I don't even have my normal whiteout. I have this cheap stuff from Meyer because I couldn't even get the whiteout from the college before they closed. So f prime of x is equal to 2x plus 6. I actually know this is a line with a slope of 2 and a y-intercept of 6. So that could help me graph this also. But I do know that there is a 0 at x equals negative 3, and the y-intercept was 6. So here we go. All right, so this is the point where f prime of x is equal to 0. So down here, we see that this is where f prime of x is less than 0. So that means f of x is actually decreasing on that interval. And then over here, this is where the derivative f prime of x is greater than 0. So that means f of x is increasing. So this is the point right here, right? X equals 3 is the point where f of x is going from decreasing to increasing. So it's going from decreasing to increasing. So if the function is going from decreasing to increasing, remember that we said that that means that there would be a relative minimum at that point. So that means that, therefore, f of x equals x squared plus 6x plus 10 has a relative minimum at x equals 3. So that's it. That's all you really had to do. Now, by the way, you could have figured out where this relative minimum was, of course, without using calculus, because I think that you know that this is a parabola. So this is a parabola. And I know that the vertex is at x equals negative b over 2a. So a is 1, b is 6, c is 10. So that would be negative 6 over 2 times 1. So then that would be negative 3. Oh, you know what? I didn't write the negative because it was x equals negative 3. All right, it was x equals negative 3, and I didn't write the negative. So it should be negative 3, all right? So there's the same thing, and I got it with pre-calculus knowledge, but only, again, because I knew it was a parabola. If I had some weird-looking graph that I didn't know what it looked like in advance, it wouldn't be this easy. All right, so keep that in mind as well. So now let's look at another example. So if there's any questions, please ask, but I'm going to move on to the next example here. So this will be the f of x is equal to x minus 3 to the 1/3 power. So now, remember that there are a couple of things that you need to, keep in mind here. All right, so one is that we need to find the critical numbers, and this happens where three things. One, f of x is undefined. Two, f prime of x is equal to 0. And 3, f prime of x is undefined. All right, so keep that in mind that these are the 3 places where there could be critical numbers. All right, so I can see that this is just the cube root of x minus 3. So this is actually continuous everywhere. I don't have to worry about that, and I can graph y equals the cube root of x minus 3 if I want to, just to be absolutely sure that there's no discontinuities, but it just looks like, it just looks like that. So nothing out of the ordinary. All right, so now let's find the derivative. So if f of x is equal to the x minus 3 to the 1/3 power, f prime of x is 1/3 x minus 3 to the negative 2/3 power. Now here is where I would really again caution you to rewrite the derivative without a negative exponent, because if I bring this down to the denominator, now I know from looking at your tests, some of you have some trouble with bringing the negative exponents down, but it's only this part that's in parentheses with the negative exponent that gets brought to the denominator. All right, so the 1 and the 3 still stays down here, and then the x minus 3 comes to the denominator with the positive 2/3 power. So then I can see then hopefully that f prime of x will never equal 0 because the numerator can never be equal to 0. So f prime of x equals 1 over 3 x minus 3 to 2/3. If I set that equal to 0, I actually multiply that by 0. I get 1 is equal to 0, which is false. So that will never happen. All right, so this never happens. So this never happened, and this never happened. And so now I can figure out where f prime of x is undefined, and that's where the denominator of this is equal to 0. So x minus 3 cannot equal 0, so then I add the 3, so x cannot equal to 3. So x equals 3 is one of the critical numbers. Now, if you look at this, hopefully you can see that what's really occurring here is that there's a a vertical tangent line here. All right, so f of x has a vertical tangent line here at x equals 3, but the graph of f of x is still continuous. There's just a vertical tangent line there. So let's actually go ahead and then see what is going on here. And actually, you can already tell what's going on here. Can you tell that f of x is always increasing? Yeah, so since f of x is always increasing, I know for sure that f of x is not going to have any relative maximum or minimum. But if I really just wanted to verify this for sure, then I could graph the f prime of x equal 1 over 3 times x minus 3 to 2/3 power. And then I notice that, again, based on the shapes of the basic parent functions, that this has an asymptote at x equals 3. And then if I substitute some points, let's say, even if I substitute x and then 1 over 3 x minus 3 to 2/3, if I substitute like let's say a 2, I get 1 over 3 times 2 minus 3 to 2/3. That will end up being 1/3, and so that's 2 1/3. And if I substitute, say, a 4, 1 over 3 times 4 minus 3 to the 2/3, that's also 1/3. So that means that the graph looks something like this. And I can see that just looking at the graph, f prime of x is always greater than 0. And I already saw from before that f of x is always increasing. So that actually was verified by looking at the graph of the derivative. And so therefore, f of x has no relative extremum or no relative maximum or minimum. All right, so hopefully that all makes sense, but we have one more fun example here. So hopefully everyone's still here. If you have questions, just again, please feel free to ask. So here is another example. So we have f of x is equal to 2x plus 1 if x is less than or equal to 1, or sorry, negative 1, and x squared minus 2 if x is greater than negative 1. So now, remember that the critical points occur at 3 places, and one of them is when f of x is undefined, or when f prime of x is equal to 0, or when f prime of x is undefined. So we'll look at both of these 3 cases one by one again. So the only point where f of x could be undefined is at x equals negative 1. So let's find the limit as x approaches negative 1 from the left of f of x. So that will be the limit as x approaches negative 1 from the left of 2x plus 1. So that's 2 times negative 1 plus 1. That would be, well, hopefully you can see that would be negative 1. And then we need the limit as x approaches negative 1 from the right of f of x. So that's the limit as x approaches negative 1 from the right of x squared minus 2. So that's negative 1 squared minus 2. That's negative 1. So hopefully you're enjoying this, because this is just a review of showing that this was continuous everywhere, which means it's not undefined. And we've talked about that for the piecewise functions before. So these limits are equal. So therefore, the limit as x approaches negative 1 of f of x equals negative 1, and that limit actually was equal to f of negative 1. So therefore, f of x is continuous everywhere. So that means that there are no points where f of x is undefined. Now I need to figure out where the derivative is equal to 0. So f prime of x, the derivative of 2x plus 1 is 2. So it's 2 if x is less than or equal to negative 1. And x squared minus 2, the derivative of x squared minus 2 is 2x. So it's 2x if x is greater than negative 1. So now I need to see where this is actually equal to 0. So the 2 can never equal 0, but 2x could equal to 0. And if I divide by 2, x could be equal to 0. Now, the other thing that you need to be careful about is that this interval is negative infinity to negative 1, and this interval is negative 1 to infinity. And you need to make sure that the number you get is in the interval, but 0 is in the interval from negative 1 to infinity. So x equals 0 is a critical point. And then 2 and 2x are actually defined everywhere. So just so you know, that actually means that the derivative is never undefined. So there are no points where the derivative is undefined either. Now, the derivative is not continuous, but the derivative is always defined. All right, so if I want to graph f prime of x, then when x is actually less than or equal to negative 1, the y value is 2. So here is the 2. Oh, and I actually just don't know why I drew the whole thing. All right, there we go. So there's that part. And then when x is greater than negative 1, the derivative is equal to 2x. So at negative 1, 2 times negative 1 is negative 2. So negative 2. But that needs to be an open circle because this was only for x is greater than negative 1, but not equal to negative 1. Then at 0, I have 2 times 0 is 0. And at 1, I have 2 times 1 is 2. So here is the line right here. So now, keep this in mind that 0 was the critical point. X equals 0 was the critical point. Well, think about this here. Here is where f prime of x was positive. Here is where it was negative. And here is where it is positive. So I'm only talking about the spots where the graph is going from positive to negative or from negative to positive. Now, you should think about this, though, because if you look at this, negative 1 wasn't a critical number, but the derivative is still going from positive to negative here. So what exactly is going on here? Well, here is the graph of f of x. All right, now think about it. Even though the derivative is undefined at that not undefined, it doesn't exist at the point. All right, so there's a difference between being undefined and not existing at the point. So we know that the derivative doesn't exist there because the derivative from the left of negative 1 is not the same as the derivative from the right of negative 1. So the derivative from the left of negative 1, does not equal the derivative from the right of negative 1. So even though the derivative doesn't exist, like that's different than just saying that it's undefined. So that's where the tricky part is, in my opinion. All right, so I think that's just because of the terminology that is used, that if you wanted to think of it like this, then of course you would have said x equals -1 here because the derivative didn't exist there. But if I'm talking about undefined, I mean like points where the derivative is not defined, but it is defined here because f prime of -1 was 2. So it does exist there, right? It does exist, but the right and the left hand derivatives are not the same. So keep that in mind as well. But if I look at the graph of f of x, though, remember when x is less than or equal to -1, I have a line, so that's 2x plus, look, here is 2x plus 1. So that looks like, well, what does it, okay, that looks like this. And then the other part of the graph was a parabola, and it looked like this. But you see the sharp corner here, where the graph changed from the line to the parabola. That sharp corner should tell you something. That sharp corner tells you that the derivatives from the left and the right of -1 are not the same. All right, so remember that's what we got from the sharp corner here. But that means that we can still, though, tell that there is a relative maximum and a relative minimum here. So here is the relative maximum at x equals -1, and there's the relative minimum at x equals 0. All right, so hopefully you enjoyed this section here on the first derivative test. So I'm going to